Oh, hey. All right, we're coming to the end of chapter 12. This is part C. A was really super, super long. B was a bit shorter, but there's also problems in there to solve. That's really the only math. So part C here, this is going to be just concepts, okay? So we have 4 objectives here. Student will be able to explain how a solute affects the colligative properties of a solution, okay? Student will be able to explain boiling point elevation. Student will be able to explain freezing point depression. And student will be able to explain the process of osmosis. I chose these particular topics because this is involving, if you want to go on into AP Chem or AP Biology, or in some cases, you know, the real world. So let's go ahead with it. Colligative properties. I gotta be honest with you, first time I heard colligative, I'm thinking Colgate the toothpaste. It's not. Colligative properties are properties of a solution that depend only on the number of solute particles present. So this is not true for every solution out there. There are properties that depend on how many solute particles. Now remember, every solution has the solute that gets dissolved and the solvent that does the dissolving, okay? So colligative properties are properties of a solution that depend only on the number of solute particles present, okay? That's it. That's all we would have to worry about for colligative properties. So it's depending on how many solute particles that there are, okay? So let's look at some examples, real-life examples of colligative properties. So here we got boiling point elevation. The more concentrated the solution is. Now wait, how do you get a solution to be more concentrated? You add more particles of solute, the stuff that gets dissolved. Okay? And that's a pretty important idea. So boiling point elevation, well wait a minute, what do we mean by boiling point elevation? Well, let's say we got water, okay? Water normally boils at 100 Celsius or 212 Fahrenheit. So that's the boiling point of water, where water goes, instead of being a liquid, it turns into a gas, it becomes steam, okay? Now, imagine if we could lift the boiling point elevation. In other words, instead of having water boil at 100 Celsius, maybe we ought to have it boil at 120 Celsius. Now, I don't know the conversion, okay, on this, but I'm just going to go ahead and say 250 Fahrenheit. So the idea, ladies and gentlemen, is when we elevate the boiling point, we're raising the boiling point of the water. Well, what does that mean? It means it's taking longer and it's going to need more energy to get the water to boil at 120 Celsius compared to 100. Okay? Now that's a colligative property, boiling point elevation. Okay? And you may notice right here, here's a picture of somebody that their car broke down. What's up with that? Well, one of the things, there is a mixture of water and something else in the radiator of the car, okay? And the reason why you have a mixture instead of pure water, it allows us to raise the boiling point, okay? The boiling point elevation, the more concentrated the solution is, the greater the boiling point elevation. That's the general idea. Now, it doesn't work the opposite way. Can we actually lower the freezing point? Yes, absolutely. We can drop the freezing point of something. That's why we call it freezing point depression. Now, let's say water is at 0 Celsius, that's when it freezes, or let's say 32 Fahrenheit. So that's the freezing point of water in Celsius and Fahrenheit. If we drop the freezing point, now let's say it's minus 5 degrees Celsius, and here it is at 20 Fahrenheit. That's what we mean by dropping the freezing point depression, And that's what the antifreeze is. It lowers the freezing point. It depresses. Depress, not I'm feeling sad. That's one kind of depression, but when we say depression, we're lowering it. We're putting it down, okay? So we're dropping it from 0, okay, down to -5 Celsius, or let's say from 32 Fahrenheit down to 20 Fahrenheit. Yeah, can you imagine that? But we actually have that, because you can go to the auto parts store and get something like this, where you have a coolant and an antifreeze that's mixed into one solution. That's really cool. You can do that. That, guys, that is the solute, okay, that you mix in with the water in the radiator of the car. You don't pour only this into the radiator. You have to mix it with the water in order for the water to go have a higher boiling point and a lower freezing point. Okay? Case in point, here's one, real facts, real world chemistry. World War II, Germany attacks Russia, 1941. Everything is going great for the Germans, except now it is December 1941. It is the coldest winter in like 50 years out there. Now the Germans had their tanks and their trucks and all that other stuff, but the problem was the winters were so cold that the fuel inside the tanks and the trucks were frozen. And they couldn't start the engine. There was no, not happening. Why? Because the fuel was frozen. Okay? So what did they have to do? They had to go and build a campfire, crackle, crackle, underneath the fuel tanks of the trucks and the tanks to melt the fuel to go from solid back to a liquid so they could, in order to start that again. That was a major thing. And yes, the Russians did take advantage of that weakness. But that's what happens with colligative properties. We can look at boiling point elevation and freezing point depression. Okay, remember, colligative properties, those are the properties where it depends on how many particles of solute you have. Okay? All right, let's move on. Now, here's a biology part called osmotic pressure. If you're going to go into AP Biology, I will guarantee you, you will work with this. Osmosis is the process in which a solvent moves across a semi-permeable membrane. Ooh, let's look at this word right here. Semi-permeable. Let's break it down. Semi means part or partly. Okay? Permeable, going through. Okay, oops, there we go. So when we say something is semi-permeable, we're saying it's only letting some of the stuff through, not all of it. Okay, so when we look at osmosis, that's the process where a solvent moves across a semi-permeable membrane. Okay? Well, what's going on with this? Why would that matter? If we're mixing like water and salt and we're trying to see what happens, why is this osmosis even happening in the first place? Great question. And this is it right here. It's making whatever is on the inside equal to whatever is on the outside. Okay? Now, does it always work? No. No, it doesn't. But this is a very important idea. Okay? Because for living things would like to be equal, even. Okay? You have an inside system and an outside system. Okay, in osmosis, that's the process where the solvent will move across the semi-permeable membrane. Well, what would be an example of a semi-permeable membrane? This, your skin. Yeah, Your skin is an example of a semi-permeable membrane. Okay? So, let's go ahead. Okay, I gotta erase all this. Yeah, I'm going through and I'm saying more things, and there's actually fewer slides, and go figure that one. Okay, but this is a really key thing for you guys in AP Biology. Okay, so when we look, all right, the osmotic pressure itself of a solution is the amount of pressure required to prevent that osmosis from happening. So what's going on here? You have osmosis. That's the process where some solute is going across a semi-permeable membrane to get to the other side. That's the idea. Now, the thing is, there's something holding that back, trying to prevent that from happening. That's what they call osmotic pressure. All living things have it. Cells have it. Living things have it. Okay? It's natural. Now, there's three possible situations that you have regarding osmotic pressure and the concentration. There's hypertonic, hypotonic, and isotonic. Those are the three things. Hypertonic, hypotonic, and isotonic. Well, let's take a look here. So this is an example where we have a red blood cell. Now, that red blood cell is what carries the oxygen in the form of O2 throughout our body, okay? We have about between 50 to 70,000 miles of blood vessels. Yeah. So with that, now it's a question of, all right, we've got a salt concentration, okay? So there's salt inside the red blood cell, there's salt outside the red blood cell. Let's just say with that. Now, the cell itself is semi-permeable, okay? It's not just letting any old thing in. Now, the thing is about the osmosis is that there's water that's going in and out, all right? So when we look at hypertonic and isotonic and hypotonic, this is where we start looking and seeing what's going on. So I'm going to compare that, the in versus the out. Inside versus outside. Okay? So we have the in versus the out. So what's going on here? So we have the salt that's inside compared to the salt outside. Okay, and we're going to do the same thing here. Now, here's the thing. When it's isotonic, the salt in is equal to the salt out. So the concentration's the same. So water's able to flow through, no big deal. If some of it goes in, some of it comes out. That's a semi-permeable membrane. This is pretty normal. This is what our red blood cell should be doing. We should be okay with that. Now, what's happening here? Okay? The deal is this. You notice how the water is rushing out of the red blood cell into the surroundings. So wait a minute. Which one has more salt? The outside has a lot more salt compared to the inside. So why is the water rushing out? It's rushing out of here because there's so much salt on this side. It wants to make the salt in here and out here equal. Which means there's so much salt out here, not that much salt in here. The water rushes out of that red blood cell to mix with that salt to make it equal. Here comes the problem though. This, losing the water, shrivels up. It shrivels up and it's dead. It's useless. It won't do anything anymore. It's become dehydrated because it's lost that water. Now, the water coming out, will that make the salt equal outside and inside? No, it won't. Typically, it will not. Okay? So, our isotonic, it's equal. Okay? Hypertonic, it's not equal. There's too much salt on the outside compared to the inside, and the water's got to rush out in order to try to make it equal. Okay, then what about hypotonic? Hypotonic is a bit different. Hypotonic is the absolute opposite. Okay? What's happening is that the salt in is much greater than the salt going out. Now remember, the salt outside versus inside. Now, here's the thing though. When you're looking at it, remember, isotonic is what is perfect. This is normal. This should be normal for us if we want our red blood cells to work right. Right? Okay? This is where the chemistry is coming in. So now you've got this water coming in. You've got a lot more salt on the inside compared to the outside. So in other words, hypotonic is the exact opposite of hypertonic. So what does that mean? Well, water's going to be coming through, and then pretty soon it bursts open. I'll demonstrate. The red blood cell pops, and now that's dead. It's no longer usable anymore for us. Okay? So, with that, ladies and gentlemen, let's do a quick recap of what we have been doing. Okay? We have spoken about colligative properties. Those properties of solutions that depend on how many solute particles we've got. And in that, real-life examples of these colligative properties, we can raise the boiling point, we can lower the freezing point. Again, based on how many particles of the solute that we have. That's the colligative properties. We spent time talking about osmosis. With osmosis, okay, that's the process where you've got a solvent that goes across a semi-permeable membrane. So that semi-permeable membrane lets some things through, other things it won't. Okay? And the reason why that's happening is trying to make the inside equal the outside. Okay? And that's the ideal, that's the perfect, but does that always happen? No. No, it does not. Okay? So it doesn't always work. We talked about the osmotic pressure. How much pressure is needed to prevent the osmosis from happening? The more solute particles you have, there's going to be a greater osmotic pressure to hold back the osmosis process. Which then, when we talk about osmotic pressure, we got three things happening. Hypertonic, hypotonic, isotonic. Okay? So, we looked at that and we compared the inside of red blood cells with the outside. Isotonic, it's equal inside and outside. Everything is great. Everything is working the way it should. However, when you look at hypertonic, there's way more salt in our example outside than inside, so the water is rushing from the red blood cell to go to the outside to mix with the salt on the outside to make it like isotonic. It's not going to happen. It wrecks the red blood cell. It basically destroys it. You have the opposite, where there's too much salt on the inside compared to the outside, and water's now rushing in to try to make the inside equal like the isotonic. The inside equal with the outside, that's isotonic. Okay? And with that, ladies and gentlemen, that is the end of chapter 12. Okay? So, you guys take it easy, and I will catch you on the next time. Bye now.